let's talk about comparing means. Suppose we're interested in comparing two different brands of batteries, battery life being the variable of interest here. So we're measuring this in minutes, and I've got brand name batteries and a generic brand of batteries. My first impression when I look at these data are that the generic brand are doing a little bit better because most of these are over 200, while most of the brand name measurements are under 200 minutes. So our first line of attack for looking at these two different groups would be to compare box plots of the two. And this gives us a sense for what we're dealing with here. And the first thing that jumps out at me actually is not that the generic brand has a longer lifespan, which it does, but actually that it's got a much smaller spread. So the generic brand has a much smaller spread than the brand name. The median value is definitely larger than the median value of the brand name. In fact, the median value of the generic this is higher than the third quartile of the brand name. So we've got an idea, we got a little taste here of what's happening with these data from box plots just to start out. Now let's remind ourselves how we might do this on the TI calculator. So if we take a look at my lists here, I've already entered the data for the two lists that we were just looking at. And now I want to make the box plots. So what I'm going to do is I'm going to go to stat plot here, and I'm going to turn this first plot on, and I'm going to make it a box plot. So I got to scroll over here. You'll see that there's two box plots. Remember, this one shows us outliers. And this box plot is going to be looking at L1, so that all looks good. I'm going to come up and take a little shortcut to plot 2 here. I'm going to turn this one on as well. I also have to select the box plot option. And I don't want it to look at L1 though, I want the other data set. So I'm going to make this L2. Frequency is of course 1 here. And now I'm going to zoom 9, and that should be it. Oops, if you get this, you got to just hit enter first, then zoom 9. And there are my box plots. Now I got these big ugly axes right in my face though. Get those axes out of my face. So I'm going to go to format right here, and I'm going to scroll down to axes off and zoom 9 again. Now I got something nice to look at. And if you want to know some of the values on here, you can trace, and it's going to tell you there's our min value, quartiles. I can push down to jump to the other data set, and off we go. Pretty cool, right? So back to the slideshow. We just looked at how to do these on the calculator. Now, what does this mean? Well, the generic batteries have a median lifetime of 205 minutes in a high usage device, while the brand name batteries have a median of 189 minutes. Okay, I could have gotten that from this trace function again here. This is telling me the median. Go up here, that's telling me the other median. I could also do one var stats with something like this. Okay, oops, not one var stats. Let's do two var stats and cut to the chase here. So calc 2 var stats, and it'll do both lists for me at once. These are switched around, but that doesn't really matter at this moment. So no frequency, calculate. There we go. So I've got my means for both groups. I got one var stats for both groups in one shot. That's basically all that does. Okay, back to this description here though. So I could have gotten these numbers from the calculator. That's the point. But if the generic batteries had a mean lifetime or a median lifetime of 205 minutes and the brand name had a median of 189 minutes, in a certain sense we could say that the generic batteries perform better by 16 minutes. Okay, we also see that the spread of the generic batteries is much lower, meaning they're more consistent. I already mentioned that. But this is a simplistic analysis. We can do much better with our tools of inference, so that's where we're going next. So let's consider the difference in means for the two kinds of batteries. Once again, I would go to 2 var stats to get these numbers. Now, how do you interpret this? Kind of the same way we just did. By the way, G stands for generic, B stands for brand name. Now, this tells us that on average, the generic brand performs better than the brand name by about 18.6 minutes. Okay. Now, this was just a sample, however, and we know that sample means vary from sample to sample. So how much better is the generic brand really? Okay, this could have just been a fluke. This could have been due to random chance. Now, I can't know how much better it really is, but I can make a confidence interval. So we won't know the true difference, but let's look at this confidence interval. We call this one a two-sample t-interval. It's a t-interval because we are working with means, and not only are we working with means, but we do not know the population standard deviation for either of these groups. If we knew the population standard deviation, we could use z-scores in a normal model. Since we don't know that, we're going to do this t-model stuff. And it's a two-sample t-interval, obviously, because we're dealing with the generic brand and the brand name. Okay, so what does this look like? Well, we're looking at the difference of two means right here, plus or minus a critical value times the standard error. It's not really anything new from what we were doing before, except that we're looking at the difference in means. Okay, so I want to know how big this difference in means is, and I want to know how much that difference in means could vary. Okay, so let's talk about this standard error. Now, even though I'm subtracting the two means here, the standard error is still going to be the square root of the sum of the variances. You should think of standard error or variance as uncertainty. So I'm uncertain about what my sample means are going to look like from sample to sample for the generic brand. And I'm uncertain what my sample means are going to look like from sample to sample for the brand name batteries. And so I'm even more uncertain about what the difference in means is going to be. So this is how we calculate the standard error for the difference in means. And standard error, of course, is s over square root of n. So when you square those, you get something that looks like that. And so that was our standard error, and this is, again, the confidence interval we're dealing with. So let's talk about the critical value there, t star. Okay? Really, we want to know the degrees of freedom. So just like before, it depends on the confidence level we're talking about. Do we want to be 90% confident or 98% confident? But it also depends on the degrees of freedom. And it turns out, when we're dealing with more than one sample, the degrees of freedom looks a little scary. Okay? Don't worry too much. Technology comes to our rescue once again. So let's take a look at how we would calculate this confidence interval on the calculator. So once again, I've already got the data entered into my lists right here. So what I'm going to do is I'm going to come down to stat, and I'm going to go over to tests. I'm going to scroll all the way down, and I'm going to find the two-sample t-interval. There it is, two-sample t-int. So right now I've got the data stored in L1 and L2. I don't want to mess with the frequencies. Okay, my confidence level is already set at 0.95, so I'm ready to go. Obviously, for a 90% confidence level, you just put 0.90 right there. These data are not pooled, and we're just going to stay away from this for now. And I just go ahead and I calculate. Now look, this calculated the degrees of freedom for me right away. That's pretty nice. This is kind of funny to look at right here. How do we get those negative values? Well, what it did actually is it did L1 minus L2, or rather x bar 1 minus x bar 2. So if you subtract these two values right here, you would get a negative number. That might make it difficult to interpret this. We can still interpret it just fine, but just for the sake of sanity, let's go ahead and do this the other way around, and I'll show you what I mean here. I'm going to take a two-sample t-interval, and I'm going to do L2 first, and then L1. And this should be all I need. Ready to calculate? And I got the same result as before, except now these are positive. Okay? So there's my interval. That's what I got. So the confidence interval is 2.1 minutes to 35.1 minutes. And so what this means is that we're 95% confident that the average time the generic batteries outlast the brand name batteries is between 2.1 and 35.1 minutes. There's evidence to suggest that the generic brand will outlast the brand name. That means we should purchase these, especially if they're cheaper. So what's next? Well, researchers investigated how the size of a bowl affects how much ice cream people tend to scoop when serving themselves. At an ice cream social, people were randomly given either a 17-ounce or a 34-ounce bowl. They're both large enough that they wouldn't be filled to capacity. So this is kind of important. This is actually telling us something about whether or not we could expect these data to be normal. If it could be filled to capacity, then that means there's kind of an upper limit and this thing could be skewed left. So they were then invited to scoop as much ice cream as they liked. Did the bowl size change the selected portion size? And here are the summaries. So we've got some data here. So for the small bowls, 26 partygoers had a small bowl randomly assigned to them, and they filled it with an average of 5.07 ounces of ice cream, and the standard deviation from that sample was 1.84 ounces. Similar thing going on here with the large bowls. They had a sample size of 22, a mean of 6.58 ounces of ice cream, and a higher standard deviation here, 2.91 ounces. So what can we do with this? Well, let's state some hypotheses. We're going to test a hypothesis here. We're going to look to see if these are significantly different. Okay, so they want to know, does the size of a bowl affect how much ice cream they're going to scoop? Okay, so what do you think the null hypothesis could be here? If the null hypothesis is that nothing's different or nothing has changed, then our null hypothesis should be that these two things are the same. So let's talk about what this means right here. I'm saying that the average amount of ice cream people are going to put in a big bowl, subtracting the average amount of ice cream people are going to put in a small bowl, should be 0. And in statistics, we'll call this delta naught. Now, it's delta because delta means difference or change, and the naught has to do with the fact that this is our hypothesis. So delta naught is 0. In other words, the size of the bowl does not make a difference on how much ice cream people are going to put in there. That's our null hypothesis. Okay? And the alternative hypothesis is that the size of the bowl does make a difference. That's all this is saying. Okay? So now we can apply our tools of inference here and test these hypotheses. We'll test this null hypothesis. We'll decide whether we're going to reject it or not. Okay? So there are some conditions that we should check here before we go ahead, though. The first two are the independence condition. So it may not be true that people fill their bowls to a volume independent of their neighbors. That's kind of what I'm thinking. Like if you see the guy in front of you just like pile it on, you might feel a little more comfortable piling it on yourself, you know, or if somebody just puts a little tiny scoop, maybe you're going to put a smaller scoop too. So maybe greater control in this experiment would be required if we want to make stronger conclusions about this. But we're going to proceed with the test anyways. We're just going to show that we thought that through. Now, the randomization condition, we've got that the subjects were given bowls of different sizes at random. They said that in the problem. So these two things together are telling us that the subjects are believably independent here. Now, something that we have to consider when we're talking about two different groups, here we're comparing two means. So we want to make sure that the groups are independent. And the way I'm looking at this is that the group with small bowls and the group with large bowls, they're as independent of each other as the individuals are in the experiment. So we already talked about how independent the individuals are. And the fact that they're in their different groups, you know, doesn't make them any different. So the nearly normal condition, when we're dealing with means, we got to think about the populations as well. So we can assume that the populations are nearly normally distributed. That means you give somebody a 34-ounce bowl, there's an average amount that people are going to pile into that bowl. And some people might be a little more, some people might be a little less. And the problem stated, remember, that the bowls were big enough to where people weren't going to be tempted to fill them to capacity. If the bowls were able to be filled to capacity, then the data might be skewed left, and we can't really make this assumption here. Now, the other thing is that the sample sizes are not too small. They're not that big. Actually, if we start getting over 40, the central limit theorem kind of kicks in, and it doesn't even matter whether the populations are normal or not. But around here, we want to think that it's plausible at least. If the sample sizes get really small, like under 10, then this becomes even more important, and we should look at histograms of the samples to see that, you know, it's believable we got normally distributed populations here. So, where are we going with this? We're going to test this difference, so we need to find the standard error in preparation for our two-sample t-test. So the standard error, we already looked at that equation. Here it is again. And If we plug in the numbers, this is what we get. So again, you get this information from one var stats or two var stats. So that's our standard error. In other words, from experiment to experiment, the variation in the difference of means is going to be something like that. So now we're going to find a t-value and a p-value for the two-sample t-test. This is nothing new. We're just dealing with differences now. Okay? So this looks a little bit scary at first, but actually it's just the very thing we're testing. We're testing the difference in these two means. Okay? Our hypothesized value was that the difference is 0, and we just found the standard error a moment ago. Okay? So once again, we've got our observed values minus our expected values divided by the standard error. Okay? And this is what I get. So my t-value is 2.1039. Now remember that it matters how many degrees of freedom we have here. And that degrees of freedom formula was not pretty. So what we can do, in order to find the degrees of freedom right here, we can just do another t-interval on the calculator. Okay, so I'm going to come back to stat, tests, and I'm going to go down to a two-sample t-interval again. Now I'm just doing this. I'm doing a t-test right now, but I'm doing the t-interval to get my degrees of freedom. Now I'm not going to use L2 and L1 because that was for the batteries, and nor do I even have L2 and L1 for the ice cream social. But I do have some summary stats. Okay, so I'm going to come down in here, I'm going to clear this, and I'll take a look at what I had a moment ago. Okay, so for the first data set, y bar was 5.07. And the standard deviation, 1.84. And there were 26 individuals in that sample. Next, I've got a mean of 6.58 for the large bowls, standard deviation of 2.91, and a sample size there of 22. Okay, doesn't matter what my confidence level is right now. I'm just doing this to get the degrees of freedom. Okay, so my degrees of freedom is 34.3. Come back to here. Okay, so this was a two-tailed test. In my initial alternative hypothesis, I said that the difference in the population means is not 0. Okay, so that means I'm looking at the probability of observing a difference that's at least this far away from 0. My degrees of freedom are 34.3, and I get 2 times 0.0214. So you might be wondering, where does 0.0214 come from? Well, it comes from students' T model with these parameters. So I'll show you that one more time as well. Okay, I need to come to distribution, and we're looking at TCDF. I'm looking for an area here. Okay, so my lower bound is going to be 2.1039. My upper bound is infinity, but 100 is going to be good enough for us. And I just found the degrees of freedom were 34.3. Okay, if your calculator doesn't look like this, then it should look like this. TCDF being the function you want to work with. And we get a p-value of 0.02139. Rounded good enough right here. And so when we multiply that value by 2, you get a p-value of 0.0428. So what do we do with it? Well, with something this small, we should reject the null hypothesis. And that means it's unlikely to observe such a difference in ice cream servings due to random variation alone. There's evidence then to suggest that people fill their bowls differently depending on the size of the bowl. That's inference for 2 means.